Hi, my name is Armin Nicole Shirazi. I'm a physicist and a philosopher at the University of Michigan, and I'm going to give an online talk on what I call the Photon existence paradox. This is a talk that is based on a recent research paper that I just completed. If you ever wondered what it would be like if you could travel at the speed of light, or you wondered why special relativity tells you that this is not possible, and why at a fundamental intuitive level it tells you it's not possible, then I think this talk might be for you. I've thought about this topic for about 15 years, and recently I was able to prove as a result, which basically helps resolve the problems in this topic as well. And I will talk about this in my presentation. So it turns out that none less than Albert Einstein himself thought about what it would be like if you could ride a light beam. And in his autobiographical notes, one finds that he probably actually stumbled or discovered special relativity because he was thinking about this. He was imagining this situation, and he hit a paradox. So, as Einstein put it, what he says is, a paradox upon which I had already hit at the age of 16. If I pursue a beam of light with the velocity c, the velocity of light in a vacuum, I should observe such a beam of light as an electromagnetic field at rest, though spatially oscillating. There seems to be no such thing, however, neither on the basis of experience nor according to Maxwell's equations. From the very beginning, it appeared to me intuitively clear that, judged from the standpoint of such an observer, everything would have to happen according to the same laws as for an observer who, relative to the Earth, was at rest. For how should the first observer know or be able to determine that he is in a state of fast, uniform motion? One sees in this paradox the germ of the special relativity theory is already contained. Now, Einstein basically addressed his paradox, what you might call the light beam observer paradox, by formulating his theory of special relativity. And the way he formulated it, it starts off with two fundamental postulates. The first one being that the speed of light is independent of the motion of its source. Now, sometimes one actually hears the postulate formulated as invariance of the speed of light, that the speed of light is independent of any inertial observer. It turns out in the original paper, Einstein only postulated independence of the motion of the emitting source, and then as he was building up the theory, he showed that it implies that. The second postulate generalizes Galileo's relativity principle. Galileo had already, a few hundred years before Einstein, formulated a relativity principle, but it was only limited to mechanics. And what Einstein did was he generalized it to all of physics. And from these two postulates, he developed his special theory of relativity. What I'm going to argue in this talk now is that special relativity transforms Einstein's original light beam observer paradox into a new paradox, what I call the Photon existence paradox. And in this talk, I'm going to, talk about the paradox, describe it, and also offer a resolution to it. And it turns out the resolution has some very profound consequences for our worldview, and I will talk about that. But for now, let me first state what the paradox actually is. So, special relativity enjoins lightspeed objects from possessing some fundamental properties that naively we might have thought any physical object has to have. That this is, in other words, some of these properties that there are preconditions for even being able to say that something physically exists. And special relativity enjoins that. Enjoins is a term that is normally used in a legal context, and I'm using this purposely because special relativity, you can think of it as one of our most fundamental laws of nature, and it prohibits these properties. And so, because it prohibits these, if we didn't already know that experiment and observation that light speed objects really do exist, then we would have thought that this enjoinment implies that it's impossible for light speed objects to exist. And so if we then found out that, from observation or experiment, if we then discovered, there are photons, for example, then their existence would seem to pose a paradox. So that's the photon existence paradox. To describe it in a slightly more depth and hopefully to get you to see it better or more vividly, imagine that we were completely ignorant of the empirical evidence for the existence of light speed objects. How would we interpret special relativity? Well, what we would know, first of all, is that from the theory, from special relativity, that if something travels less than the speed of light, it cannot be accelerated to the speed of light. We would also have failed to observe any light speed objects. And then the theory, so special relativity, would also tell us that if such objects existed, then there would be certain strange aspects to them. So for one thing, you could not assign to them the origin of a coordinate system in space. And the reason for that is that in order to be able to do that, you need a rest frame. And speed of light objects cannot have a rest frame, because if they did, that would contradict the speed of light postulate. It would also be impossible to assign to light speed objects a finite observed duration of existence in spacetime. Now, this requires a little bit of explanation, but it's not hard. Consider a clock. Now, normally you would think that a clock just tells us the time, but actually, at a more fundamental level, if you change your perspective, what a clock really tells us is for how long it existed. So take a clock and you check, and let's say it says 12 noon, and then sometime later you check again, and I'm assuming the clock works fine, and I'm considering a rest frame. You check again, and let's say it says 6 in the afternoon. It's not just that the clock tells you that 6 hours passed. It tells you, actually, that between those two events, you checking the clock at 12 p.m. and you checking the clock at 6 p.m., between those events, the clock is telling you that it has existed for 6 hours. Now, in special relativity, there is a phenomenon called time dilation, where when you observe something that is moving, the rate of passage of time for them is less than the rate of passage of time for you or for a clock that is not moving relative to you. This is called time dilation. So if you have a clock that is moving, that would mean that you would observe time for it to pass more slowly, but when we switch our perspective and now think about it in terms of duration of existence, what the moving clock is really telling us is that its duration of existence between two events, the first time you checked it, what time it was, and then the second time you checked it. And by the way you would do this is, obviously, if it's moving relative to you, you have to set it up correctly. You have to have two clocks that are not moving relative to you, some distance apart, and then you imagine the moving clock to coincide with one, and then in a straight line, because it's an inertial motion, to coincide with the other one, and then you compare the clock readings of the moving clock with the clock readings of the synchronized stationary clocks. So that's the experiment. But at any rate, it would just tell you that the moving clock has a lower or lesser observed duration of existence than if it was not moving. And the faster it is moving, the less would be its observed duration of existence in spacetime between those two events. If you could have a clock moving at the speed of light, then there would be no time passing. So its observed duration of existence between the two events would be 0. And so, for example, for a photon, that means that the moment that it comes into existence, which means the moment it's been emitted somewhere, and the moment it goes out of existence, the moment it has been absorbed somewhere else, that no time passes in between. So if it was possible to jump into that frame, which it's not possible, but if it was, then you would observe that there's actually the same moment. Now, because it's not possible to jump into the frame of a light speed object, one might object to this whole analysis. And my response to that would be fine. If you want to reject this, then the position that it leaves you in is you can't even say that the concept of an observed duration of existence in space-time applies to light speed objects. It obviously applies to any ordinary object, right? Because any ordinary object, you can think of it as just put a clock next to it that is not moving relative to it, and you can always interpret any time that passes as its duration of existence. But somehow this concept doesn't apply to them, or if you want to be more generous and say, okay, it does apply, but if it does apply, that means its observed duration of existence in space-time is 0. These are properties these are aspects that we would not expect of something that exists. And so if we were in this imagined world where we had not yet discovered any evidence that light speed objects exist, these factors that subluminal objects cannot be accelerated to the speed of light, and we didn't see any speed of light objects, and the theory is telling us that there's some really strange things going on with light speed objects, then that would likely lead us to believe that it's impossible for light speed objects to exist. And then if we suddenly discovered via experiment or observation that there are photons, then that would seem to pose a paradox. And that's the photon existence paradox. So there are 3 types of paradox that can occur in physics. The first type is what one might call an error. This is a situation where the problem is not with the theory, the problem is with you, or how you use the theory. So if we misapply the theory, or if we misinterpret it, or we make some mistake in a logical or mathematical deduction, all that counts as an error. And the way to fix this type of paradox is just to simply fix a mistake. There's nothing to fix with the theory itself, because there's nothing wrong with the theory as far as this particular issue is concerned. The second type of paradox is what one might call a gap. So in this situation, the theory does have a flaw, but the flaw is not fatal. And the way to resolve this kind of paradox is to fix the flaw. So you have a theory, it has a flaw, you fix the flaw, and it resolves the paradox. The third type of paradox you could have is what might be called a contradiction. In this situation, you have a theory that has a flaw, and the flaw is fatal. You can't fix it. What you have to do in such a situation is you have to replace the theory with a new theory. And so contradictions are often associated with revolutions in physics. So to give a couple examples, special relativity has replaced Newtonian theory because Einstein noticed a contradiction. And it's kind of interesting, in the introduction to his famous 1905 paper where he introduces special relativity, he talks about how there are asymmetric feed aspects in electrodynamics that are not inherent in the phenomena themselves. And up until that point, physicists basically, at the time, there was an ether theory. People thought that there was a substance that was everywhere, and that light was basically propagating disturbance in the ether. And they were so fixated on this way that they didn't notice the contradiction. Einstein did, and it led him to the theory of special relativity, which then eventually replaced Newtonian theory. Another type of paradox, special relativity itself gave rise to a number of paradoxes, like the twin paradox, or the pole in the barn paradox, and so forth. And all of these can be classified as errors, because when one thinks through those carefully, one finds that the problem is not with special relativity. The problem is how one conceptualizes the problem, or some mistake. So, for example, the twin paradox is a scenario. You have two astronaut twins. One stays on Earth, the other one travels in space, and at a constant velocity. And then at some point, he decides to go back, and so they meet again. And then the question is this: I had already mentioned time dilation, and time dilation is kind of a symmetric phenomenon. So the stay-at-home twin would, because of time dilation, expect his traveling twin to be to have aged less, and the traveling twin, because from his perspective, the twin that stayed at home was traveling, and he was just at rest with respect to himself. The stay-at-home twin should have been aged less. And it turns out that what actually happens is that the traveling twin aged less. And a lot of people, there has been a long history of discussion on this paradox. There's a particularly tragic story by one physicist by the name of Dingle, who apparently was an authority on this, and then somehow he just got fixated on this paradox, and he thought this was a reason why special relativity was wrong. And it turns out, however, there is a very simple resolution to this. And it has to do with the path that the two twins travel in space-time. When you travel at rest, when you're at rest, the path that you travel is basically the longest path that you can get from 2 points A to B. And any other path, so if you're traveling away and then you're coming back, that path is going to be shorter. And the length of the path that you travel in space-time is proportional to how much you have aged. And so because the path of the stay-at-home twin was longer than the path in space-time of the traveling twin, that means when they meet again, he has aged more. It's a really simple resolution, but it requires one to really understand special relativity as a theory in 4 dimensions as opposed to 3. And I think a lot of people get hung up on that. But anyway, the whole point of this was to show that the twin paradox is not a gap. It doesn't mean that special relativity has a flaw, and it's definitely not a contradiction. It's simply a mistake on in some sort of a conceptual reasoning about the theory. So what kind of a paradox is a photon existence paradox? Well, I'm going to table the answer to that because I want to now focus on offering a resolution to it. And the way I'm going to resolve it is I'm going to prove another something else. I'm going to prove what I call the Ontic equivalence relation, and that will give me the answer. Now, to prove the Ontic equivalence relation, I will prove it from special relativity plus 4 space-time principles that, as far as I can tell, have not yet been really, in general, appreciated. And I have certainly not found any discussion in the literature about them, probably because they're extremely, extremely obvious. But before I do this, I want to just talk a little bit about proofs in physics. So physics is not math. In math, obviously, proofs are of paramount importance. And in physics, well, there are many things we cannot prove, but that doesn't mean that proofs don't have a role to play. They actually have a very important role to play, in the sense that if we have some really solid foundational assumptions. So foundational assumptions are assumptions that you can't derive or prove from anything else. But if we have some solid foundational assumptions, then it is only through a proof that we know that any deductions we make from those assumptions are as strong as the assumptions themselves. So in that sense, proofs are actually very important in physics. So alternative is, an extreme version of an alternative would be to have what is called a tower of conjectures. And it turns out in contemporary fundamental theoretical physics, there are towers of conjectures where you have one conjecture on top of another. And the problem with that is, of course, that if any one of those conjectures is wrong, then at the very least, it puts everything else that depends on it, that builds on it, into question. So if you have a proof, then you avoid this kind of a situation. Now, if you're, I try to make this talk accessible to a broader audience than just people who have studied physics or who are physicists. And so when you hear talk about proof, it might cause you to tune off. And I urge you to still hang in there. This proof is going to be one of the easiest you'll find in physics, I think. And it is well worth it because the result will help gain a deeper understanding at the most fundamental level about reality. And it's not just the result, but the proof itself that is important, because if you understand it, I believe it will help you see how, for quite self-evident space-time principles, for principles that we hold to be so obvious we don't actually even think about it, are actually in conflict with a notion of physical existence that we have held for likely thousands of years. So let's get to the principles then first. In modern physics, invariance and symmetry principles are very, very important, and the reason is that they tell us that aspects of things that we're considering that stay the same, that don't change, when we perform certain transformations. What are these transformations? Well, some that you might already be well acquainted with are rotations and translations. When you have rotations and boosts, then these are the Lorentz transformations. When you add the translations to that, then you get the Poincaré transformations. When you add to that conformal transformation dilations, you have what are called the conformal group transformations that are elements of the conformal group. Conformal transformations are angle-preserving transformations, where if you imagine, let's say, a rubber sheet with a grid on it, and you do certain deformations that keeps the angles still the same, that would be conformal transformation. A dilation is refers to a situation in which you change the size of an object without changing its shape. So the point is, these are all physical transformations. There are specific kinds of transformation, namely transformations of coordinate systems that you can undertake. And if you have an object in your coordinate system, you can look at how these transformations affect the object, how they might change it. For example, when you perform a translation, then you're changing the position of the object in the coordinate system. But then there are other aspects of an object that might not change, and those properties of an object that don't change, we then call invariant under those transformations. So one of the properties that is invariant under any of these transformations of an object is how many dimensions it is characterized by. It's what I call its absolute dimensionality. And this is really very obvious, right? We don't think about this. In fact, I think the reason that these four principles have, as far as I know, not been previously discussed in the physics literature is because, not because they're so difficult to understand, but quite the opposite, that they're so obvious, they're just right in front of your nose, you don't see it. But for the purposes that I have here, because I want to derive something from these four, I do need to point out the obvious. So I need to discuss them. So the the absolute dimensionality of an object doesn't change under any of these transformations. It's an invariant, and that's called the invariance of absolute dimensionality. Another invariant property of an object is whether it exists in space-time or not. So, for example, you cannot make an object cease to exist in space-time by performing a rotation. Again, very obvious, but important to point out. Now, because I'm talking about existence in space-time, and existence doesn't really, in contemporary physics, doesn't connect to physics very well, I have to say a bit more and ground it more in physics, what I mean by existence in space-time. And I will do that in the next slide. But for now, let's now just take a note that this is also an invariance of the object. Now, when I perform these operations, then they always take me from a 3+1 slicing of space-time only to another 3+1 slicing, never to something else, never to, let's say, 2+2 or, I don't know, 2+1 or something. And this reflects two separate symmetry principles, one which pertains to space and one which pertains to time. And the symmetry principles are, again, really obvious. Basically, the fact that this slicing, as a decomposition of space-time is preserved under these transformations, reflects the fact that physical space has the same number of dimensions. So when I say physical space, by the way, I mean three-dimensional space. I mean the space of our reality. As a mathematical abstraction, I can always consider, lower dimensional spaces or even higher dimensional spaces, but that's unphysical. I'm talking about the physical space that is modeling the reality that we live in, that we exist in. And so this idea that it has everywhere in the space-time, in the particular space-time, that it has the same number of dimensions, that I call the homodimensionality of space. And the idea that time also has everywhere the same number of dimensions, namely 1, I call the homodimensionality of time. And for convenience, I will define a space-time which is both homodimensional in space and in time as an isodimensional space-time. So let me go back to the invariance of space-time ontic value. I still have to, like I said, ground it in physics. I have to be clear about what I mean by an object existing in space-time. And to do that, I need a postulate, because in standard physics, in contemporary early 21st century, as far as I know, there isn't really anything that connects, or hardly anything that connects physics to existence. So I need something, and so I'm introducing a postulate which says an object exists in space-time if and only if, so the IFF it means if and only if, it is characterized by a time-like proper time. So if and only if means the implication goes both ways. So if an object exists in space-time, it is characterized by a time-like proper time, and if it is characterized by a time-like proper time, it exists in space-time. And the proper time is, remember, I had already talked about this. You can think of, I'll mention this in a moment, but let me just say, the reason I'm putting it as a postulate is because I can't derive it from anything else. I can't derive it because physics already doesn't really connect to existence. So this is my first connection point in a way. But I can offer some plausibility arguments. And the first one is that the proper time of time-like objects can be interpreted without any confusion, quite clearly as their duration of existence. And I did give an example of this already earlier in my talk. A clock, it doesn't just tell you the time, it actually, at a more fundamental level, or looked at from a more fundamental perspective, it tells you how long it has existed. And that is true whether the clock is at rest with respect to you or whether it's moving. When it's moving, then the time that passes for it, we would call this a proper time. But like I said, we can also think of it as its duration of existence between the given space-time events, let's say between the two times that you check the time. The second plausibility argument is that if space-time ontic value is based on proper time, then it is a physical invariant, at least as far as the Poincare transformations are concerned. So these give at least an indication that this is a good existence criterion. So the space-time ontic value is 1 if an object satisfies this criterion, and it's 0 if it fails to satisfy this criterion. So now I'm going to start deriving or proving the big result, which is called the Ontic equivalence relation, from these 4 principles and special relativity generalized to n+1 dimensions. Let me first state the result. What it means I will talk about later. It says that existence in spacetime is an equivalence relation by absolute dimensionality. So again, if you're not mathematically inclined, you might think that you want to skip this, but I encourage you to at least listen to this and see if you can get any takeaway from it, because if you can understand this, it will show that the 4 very obvious principles that I just mentioned are incompatible, plus special relativity, that they're incompatible with the notion of physical existence that we have literally held for thousands of years. So I encourage you to still stay on. Alright, so to prove the equivalence relation, I have to prove any equivalence relation, one needs to prove that 3 properties are satisfied. These properties are called reflexivity, symmetry, and transitivity. And in order to prove this, I first have to set up the situation, right? And that's what I'm doing now. So I start off by supposing that there is an m-dimensional object A that exists in an n+1 dimensional region of spacetime. At this point, I'm not making any assumptions about what m or n are. I don't assume in particular, not yet, that they're the same. And I'm only considering a region of spacetime as opposed to like all of spacetime. I do assume, however, that the 4 principles hold and that special relativity holds. Alright, so we know by assumption that the spacetime ontic value of A, in this region at least, is 1, because that's how we started off with. And so the next question then is to ask, what is m? Obviously, the dimensionality of the object cannot be greater than the dimensionality of the region that contains the object. So you can't have that m is greater than n. So that's very obvious. But it turns out it can also not be the case that m is smaller than n. And this is a lot less obvious. This is because, in special relativity, time dilation and length contraction are coupled to each other. You can never have one without the other. And the 2 invariance principles extend this to the situation where you basically lose a dimension. You cannot lose a dimension without also turning the space-time ontic value from 1 to 0. What basically holds us together is the fact that when you have a complete length contraction or complete time dilation, in both cases, the Lorentz factor becomes infinite. So, if you had a situation where A had fewer dimensions than the region, the space-time region, fewer length dimensions than the space-time region in which it exists, or it's supposed to exist, then you would have a situation where, at least along one direction, A was completely length contracted. And by the coupling that I just mentioned, that means that it's completely time dilated as well. But complete time dilation means its proper time is no longer time-like. And if its proper time is no longer time-like, that means that its space-time ontic value is no longer 1. And that means that actually this contradicts the starting assumption that we made, which was that A exists in that space-time region. So it cannot be the case that M is smaller than N either. So if M can't be greater than N, and if it can't be smaller than N, then the only possibility left is that it is equal to N. But it's only equal to N in a particular region. But then, notice we had 2 other principles that we're going to use now, the 2 homodimensionality principles, and we assume they hold. That means the space-time that we're considering is isodimensional, and so that means the dimensions of space and time don't change from region to region. They're the same everywhere. And from that, we know then that the space-time everywhere has the same number of space and time dimensions as the regions that we considered. So the n plus 1 dimensional region is in fact all of the n plus 1 dimensional space-time. So that sets up the proof, which is now extremely simple. Remember, we have to prove reflexivity, symmetry, and transitivity. To prove reflexivity, it's just basically enough just to recognize that A exists in the space-time in which it exists. To prove symmetry, we consider another object that is m-dimensional, and the same arguments that we gave before tells us that this m-dimensional object B must exist in an m plus 1 dimensional space-time. And now we suppose that B exists in the same space-time as A. If symmetry holds, then that implies that if B exists in the same space-time as A, then A exists in the same space-time as B. And we know that this is true because if B exists in the same space-time as A, then m plus 1 is equal to n plus 1. And there's an equality between the two. Equality is the strictest form of equivalence, so it already implies symmetry. So symmetry follows right away. To prove transitivity, we consider a third object, C, which is L-dimensional. And again, by the same argument I gave in the previous page, it has to exist in an L plus 1 dimensional space-time. And now we suppose that A exists in the same space-time as B, and B in the same space-time as C. So transitivity means then that if that is the case, then A has to exist in the same space-time as C. But that actually is the case, because all we have to show is that, this, what I just said, implies that m plus 1 is equal to m plus 1 is equal to L plus 1. And again, equality being the strictest form of equivalence implies transitivity, and so transitivity follows at once. So all three conditions are satisfied, and that means that existence in a space-time is an equivalence relation by the number of length dimensions that characterize an object, by its absolute dimensionality. All right, so that's the result, but what does it mean? To understand the implication of this Ontic equivalence relation, we have to first recall that every equivalence relation on a set partitions that set into equivalence classes. So basically into separate cells, such that no member of the set is a member of two cells at the same time. There's no overlap between the cells. And considered now in this situation, the Ontic equivalence relation, because it pertains to physical objects, right? It partitions the set of all physical objects, or in other words, all the objects that are in the domain of physics, into equivalence classes, and it sorts them essentially by it partitions them, separates them out by the number of length dimensions, so that each equivalence class only exists in a space-time such that the number of dimensions of the space-time, length dimensions of the space-time, matches the dimensionality of the object. So in other words, three-dimensional objects can only exist in a 3 plus 1 dimensional space-time, and 3 plus 1 dimensional space-time can only contain, or can only have three-dimensional objects existing in them. And the same for 2, 4, whatever. And so from this, we can then immediately recognize that Lightspeed objects do not exist in 3 plus 1 space-time, but in a 2 plus 1 space-time. And the reason is because Lightspeed objects are completely length contracted along their direction of motion. So they have one dimension fewer, so 3 minus 1 is 2. They're two-dimensional. And by the Ontic equivalence relation, the space-time that they can exist in has to be 2 plus 1. It cannot be 3 plus 1. It cannot be the space-time in which we, the space-time observers, exist. Now, 2 plus 1 spacetimes are used a lot in theoretical physics as toy models and kind of playgrounds to test out theories in a simplified setting so that people can explore how their theories work out before they go on to the real thing. And as far as I know, there's never any claim that these 2+1 spacetimes in such time models really are supposed to exist. There always seems to be the understanding that this is just a mathematical simplification. But here I'm taking the opposite stance. I'm saying what the Ontic equivalence relation tells us, there really is such a thing. That 2+1 spacetime has exactly the same footing as a physical space as our 3+1 spacetime, what I call our repository of existence. They're both on an equal footing. It's just that we don't have access to it because, well, we don't exist in 2+1. So once you understand this, basically that resolves the photon existence paradox. Lightspeed objects do not exist in spacetime but in area time. So all the problems, remember, what motivates the paradox is that special relativity does not allow for lightspeed objects to share some of the fundamental aspects that we naively thought, every physically existing object has, right? So let's go through a few of them. The reason you cannot accelerate to the speed of light is because if you could, you would no longer be a space-time object. You would be an area-time object. And remember, the space-time ontic value is an invariant. It can't change. You can't change. The reason that lightspeed objects cannot be pinned, that you cannot pin the origin of a coordinate system in space to lightspeed objects is because the coordinate system has a wrong number of dimensions. You need a coordinate system that belongs to a space that has one dimension fewer. So when you're talking about space, it has to be just a two-dimensional space. So the coordinate system has to belong to a two-dimensional space. By the way, it's important to distinguish between the coordinate system and the underlying space. The coordinate system is always arbitrary. The space is not. So I'm talking about the space, right? So the coordinate system follows what the space is. So if the space is two-dimensional, that means the coordinate system has to be two-dimensional. And that's the coordinate system that you need to represent such objects in. Now you might ask, well, what is this two-dimensional coordinate system for lightspeed objects? It seems to me, this is still something I'm working on, but it seems to me that the coordinate system, that the space is a space that has some relationship, an isomorphism to the null plane that is normal to the direction of motion of the lightspeed object. So if you consider a lightspeed object, you can think of it as being embedded in a plane, an infinitely extended plane that propagates at the speed of light in the same direction. So its normal direction is the same direction as the object that it propagates, and this plane would be basically isomorphic to the space in which the object exists. And then you cannot assign to light speeds any finite observed duration of existence, or if you want to even reject saying that you cannot even apply the concept of observed duration of existence. Either way, you can't do this because they don't exist in space-time. They exist. Lightspeed objects exist in area time. So that resolves the paradox, but it doesn't yet make clear exactly what type of paradox it has resolved. Remember, a paradox can be either due to an error, or a gap, or a contradiction. So it turns out that there is a little bit of ambiguity that depends on what one wishes to emphasize. So let's start with thinking about the photon existence paradox as an error. If it was due to an error, there had to be an error somewhere. The error was a very subtle one. I call this, the error was an assumption that we hold so deeply, I think most of us, that we are not even aware of it. I call this the assumption of absolute existence. And what I mean by this is this idea that the existence of a physical object can be specified without any reference to an n plus one dimensional. So I put here n dimensional spacetime. I should have put n plus one dimensional spacetime. That's a typo. So the assumption of absolute existence seems to be so deeply ingrained that we don't even think of any alternatives. I think this is the reason why when I first present this idea to other physicists, they have difficulty understanding this. An alternative never popped in. This is an assumption that we have held likely for thousands of years. I don't think that even the Greek philosophers ever thought, if a space is three-dimensional, does an object exist, also in a two-dimensional subspace, or anything like that. It would have just seemed completely obvious that, it has to be the case that if it exists, then certainly it exists in the space in which we exist. And it turns out that is not true. The alternative notion to that is relative existence. So relative existence refers to the idea that if you're going to specify the existence of a physical object, you have to also include in that specification a reference to which n plus one dimensional spacetime it exists in. So you have to include the spacetime as well. And so here's once you understand this distinction, I can also very quickly explain the difference between an invariance and absoluteness. So existence, the spacetime ontic value is invariant in the sense that for any space, let's say for any observer in a particular spacetime, it doesn't change, through any of these. But it is not absolute because like we saw, because of the Ontic equivalence relation, you can only one of the possible n plus one dimensional spacetimes in which any given object exists. It can't exist in in more than one, because that would violate the equivalence class structure that is associated with physical existence. So this is then, if you want to think of the photon existence paradox as an error, this is the error, that we assume that, we can just, it is enough just to say that a physical object exists. And it turns out it's not enough. You also have to specify what spacetime it exists in. It turns out that, if that special relativity gave us indications that this assumption of absolute existence is false. But they were very subtle, and so we didn't recognize it. I think it's important, by the way, to point this out, because let's say if special relativity gave us indications that absolute existence is actually correct, then that would be a problem, because you would have, one part of the theory basically affirming absolute existence, another part of, basically saying that it's wrong, and that would essentially be a contradiction, and it would mean that special relativity potentially might be wrong. But it turns out that's not the case at all. Special relativity was telling us, albeit in a very, very subtle manner, that absolute existence is false. So one of these indications is that the integral of any volume of space in the light-like direction is zero. And if you don't see why this gives any indications that absolute existence is false, it shows you just how subtle this indication is. So let's break it down. If absolute existence is correct, and let's say that we assume that photons exist, we don't care about where it exists or whatever, because we're assuming that absolute existence is true. So if a photon exists and absolute existence is true, then it implies immediately that it exists in spacetime. And if it exists in spacetime, then it should be possible to take a region of space and integrate it along the spacetime path of the object, the photon, let's say, and obtain a finite space-time volume. But the mathematics is such that whenever you integrate the volume of a spatial region in the light-like direction, you get zero. You never get a four-dimensional volume. And so it turns out by making, if you have a conditional and if-then statement where you start off with an assumption and it leads you to the wrong conclusion. The wrong conclusion here being you should be able to integrate the spatial region along the space-time path to obtain a finite four volume. That turns out to be false. That means something was wrong with your original assumptions. And the original assumption here was that absolute existence was true. So there wasn't examples. There were indications already in special relativity, even without talking about existence, that absolute existence is wrong. But it was just too subtle, and so we didn't see it. But the point of all this is that relativity actually gave us the right indications all along. We just didn't see it. So the mistake was on us. We made the mistake. The flaw was not with relativity. If you want to frame the paradox in this way, then definitely the photon existence paradox was due to an error. And fixing the error means, fixing our mistake. In this case, it means letting go of an assumption that we've held literally for thousands of years, a fundamental assumption about existence, and replacing it with a different one, with the notion of relative existence. But because for over 100 years, basically the entire physics community was not able to recognize these extreme subtle indications of special relativity, then that opens the possibility also to think of the photon existence paradox as a gap. So a gap, remember, is a flaw that in the theory, but a flaw that is not fatal. If you think of the paradox in this way, then the flaw in standard special relativity is that it lacks any reference to the concept of existence. So all you had were the indirect hints, but the indirect hints that light speed objects do not exist in space-time were way too subtle, and so we didn't recognize them. And to conceptualize how the gap is bridged, how we fix the problem or the result of the paradox, remember, the existence criterion was necessary to prove the Ontic equivalence relations that gave us basically the unequivocal resolution. However, if you adopt the existence criterion, you already know directly from it. You don't even need the Ontic equivalence relation. The existence criterion by itself will tell you that light speed objects do not exist in space-time, because remember, the existence criterion says an object exists in space-time if and only if it is characterized by a time-like proper time, and light speed objects are not characterized by time-like proper times. So you already know this directly. So amending standard special relativity with this existence criterion, so adding that to the theory, you can think of it then, fixes the gap. It closes the gap in special relativity. So the bottom line is, whether you want to think of the paradox as being due to an error or due to a gap just depends on what you want to emphasize. If you want to emphasize our inability to recognize the very subtle hints from special relativity, then you would think of it as an error. And if you want to emphasize that there was something missing in standard special relativity, namely its reference to the concept of existence, then you would think of the paradox as a gap. One way that you cannot, and I want to be very, very emphatic about this, one thing that you cannot, one way that you cannot characterize this paradox as is in terms of a contradiction. There is no fatal flaw in special relativity. The lack of a concept of reference does not amount to something that kills the theory. So, one last thing I'd like to mention is, alright, so we now know photons or light speed objects do not exist in space-time, but that by itself doesn't yet tell us, if you don't consider the Ontic equivalence relation. Absent that, it doesn't yet tell us that light-speed objects exist in area time. You could imagine a situation where you try to eliminate them completely. For example, if you think of any interactions that involve light-speed objects in terms of changes in energy or momentum between objects that are a distance ct apart. So ct means, it takes the speed of light to, it's a distance that a light speed object traverses in the time t. Any interactions between objects where the energy or momentum change is anti-correlated. So if the energy of one, let's say, goes up, the energy of the other one goes down by the same amount, and they're away a distance of ct. So a time t passed, before you saw these effects, you could try in principle eliminate light speed objects entirely. And what you would have an action at a distance theory. So if you're willing to put up with that, you would be able to eliminate them. But it turns out that special relativity actually gives a hint that light speed objects exist in area time. And again, it's very subtle. So the hint is as follows. If you consider the speed of an object as it approaches the speed of light, its direction of motion and its time direction both approach the light-like direction. So if you were to approach this graphically, it would look like the horizontal and vertical axis zeroing into towards the diagonal. And in the limit of the speed of light, the two directions can be thought, you can think of them as having merged along the light-like direction. But that means that space-time, when you consider it now as a vector space, has become linearly dependent because you had two basis vectors below the speed of light. In the limit now they're both light-like. And so linear dependence in general means that there are too many dimensions. So the 3+1 spacetime has actually one too many dimensions. And when you want to reduce, if you want to reduce then 3+1, there are only two ways to do it. Either you go from 3+1 to 3+0, or from 3+1 to 2+1. And you can eliminate 3+0 because we know that light speed objects have only two space-like degrees of freedom. So there was a subtle hint, we just didn't see it. So to conclude this talk, I want to quote another paragraph. This passage follows immediately the other passage that I quoted at the very beginning, where Einstein was recalling his recollection from the paradox. And he said, "Today, everyone knows, of course, that all attempts to clarify this paradox," this was now Einstein's light beam observer paradox, to clarify this paradox satisfactorily were condemned to failure as long as the axioms of the absolute character of time was rooted unrecognized in the unconscious. To recognize clearly this axiom and its arbitrary character already implies the essentials of the solution of the problem. So what strikes me is that I believe the Ontic equivalence relation is eventually going to be widely known, accepted. Now, how long that will take, I don't know. But the reason why I'm very certain that it will be accepted eventually is because, for one thing, the starting assumptions are very solid. You have four obvious or self-evident principles, space-time principles. You have special relativity. So there couldn't be hardly a more solid basis from which to derive any result. And the proof is really, really straightforward and simple and easy to check. So for that reason, I think it will eventually be recognized in general. How long it takes is more, I think, a function of sociological or psychological factors than of the physics. But once that happens, once it becomes widely known and accepted, it's striking to me that this very quote could also then refer to the photon existence paradox if you substitute existence for time. So there is a parallel there then. In the early 20th century, there was a groundbreaking idea that there is no absolute time, which forever changed physics. And I believe in the early 21st century, there is now another implication which is actually tied to that, namely that there is no absolute existence, which is going to have groundbreaking effects. And the beauty from my standpoint is the implications of these, for the most part, haven't been worked out yet. So it's like opening a completely new area of study, a completely new arena of physics that we didn't even know was there. So I hope you enjoyed the talk, and I wish you a wonderful day.